Ladies and gentlemen, please welcome Vice President of Global Infrastructure at Amazon Web Services, Peter DeSantis.
Welcome to Tuesday Night Live. Thank you for coming. Hope you guys enjoyed Kinky. Great band. Let's give it one more round of applause for Kinky. Awesome. Well, I have to start off with an apology. Now, when I agreed to do Tuesday Night Live, I specifically asked to have beer served during the keynote. However, I've been informed, due to a logistical problem, that's not going to happen here tonight. So, hold on. First of all that beer that was going to be served tonight, we're going to add to replay, for one. Two, if I do this again next year, I promise there'll be beer. And three, I really do hope that you had a chance to get a cocktail over a beer before the show, because I am told that I am much more interesting after a couple drinks. So, welcome to Tuesday Night Live, or Keynote Eve, as I like to call it. We've got a bunch of fun things to talk about tonight, and given we don't have beer, I want to get right started so we get out of here on time. All right, I figured a great place to start the evening would be to update on our global infrastructure. One big value proposition of AWS is access to our global footprint. You can write your application once and deploy it to any region in our whole global infrastructure. Going global has never been so easy. Now I'm going to walk you through the timeline of our region expansions. What you see behind me is what AWS looked like after our first 5 years in business. We had 4 regions. We launched our first region in Northern Virginia, followed by our first European region in Dublin, followed by our second US region in Northern California, followed by our first Asia Pacific region in Singapore. Now, this may not seem that impressive, but I promise you, at the time, this was a really big deal for us. But let's keep going. Now I've illustrated what AWS looked like after our second 5 years. You can see that we've added 7 additional regions. We added 2 in North America, Oregon, and a special region for certain government workloads, US GovCloud West. In South America, we added Sao Paulo, and we added our second region in Europe with Frankfurt. And then we added 3 regions in Asia Pacific: Beijing, Tokyo, and Sydney. So all told, in the first 10 years, we launched 11 regions. Now, let's look at 2016, 2017, and what we've announced that we'll be launching in 2018. In this 3-year period, we will add another 11 regions. This is as many regions as we launched in the whole first 10 years of our existence. And we're just getting started. I fully expect the pace of global expansion is going to continue to accelerate. Okay, let's review the bidding here. We've launched 2 new North American regions, Ohio and Montreal. We launched our 3rd European region in London, and we launched 2 new regions in Asia Pacific, Mumbai and Seoul. In addition to that, we pre-announced a second GovCloud region in the US GovCloud East. We've also pre-announced 2 additional European regions, one in France and one in Sweden. And we've pre-announced our first Middle Eastern region in Bahrain. Additionally, we'll be launching in Hong Kong. So all total, 11 new regions in the last year, this year, and next year. Okay, this is probably the perfect time to touch briefly on sustainable energy and our efforts there. If you caught this talk last year, James Hamilton discussed our long-term commitment to achieve 100% renewable energy and our progress towards that goal. I won't have time to go too deep in this tonight, but in addition to these renewable projects, our goal is to build AWS regions in locations where we can supply them with renewable power in the same grid. Take Sweden, for example. We're very excited to be launching in Sweden with another major European region. And the reason for this is Sweden's, amongst other reasons, is Sweden's commitment to renewable energy. Sweden currently produces about 50% of their energy from renewable sources, which is one of the highest in all of Europe. In addition to that, Sweden has made the most aggressive public commitment to get to 100% renewable power in all of Europe. And we're happy to be part of that with them. Now, let's look at Bahrain. When we looked at the Middle East, the power infrastructure in the Middle East is not as advanced as other areas of the world in terms of renewable energy. So therefore, when we looked for a site, we were excited to partner with Bahrain to launch the first utility-scale renewable project. The energy produced from this project will help power our Bahrain region once operational. So it's another great example of how sustainability is factoring into our regional expansion strategy. Okay, I've shown you the expansion of regions, but now let's take a moment to see what a region is. We're going to zoom in a little here. What we talk about when we talk about a region is very different than what you might hear from some other providers. And so I want to spend some time clarifying what a region is. Okay, it all starts with something we call an availability zone. An availability zone is a very important concept for us. Each availability zone is a fully isolated partition of our infrastructure. What do I mean by fully isolated? Well, first, it's physically separate. Not in the same building as other availability zones, not across the street from other availability zones. It's separated by meaningful distance. You can think in terms of miles here, and usually several miles. We also design each availability zone to have its own power infrastructure. Availability zones are also quite large. As illustrated here, they can be more than one data center, and they can be 100,000 servers or more at full scale, many hundreds of thousands of servers. Okay, so again, we have 5 data centers making up this availability zone behind me. When we have that, we connect these availability zones via fully redundant and isolated metro fiber. This provides extremely high reliability of connectivity between those facilities within the availability zone. Now, let's look at how availability zones get composed into regions. Each region, as I said, is multiple availability zones. All AWS regions have at least 2 public availability zones, and most have 3 or more. Our largest region currently has 6 public availability zones. Now, let's pause our anatomy lesson for 1 second. Before we wire up all these availability zones to each other, I want to explain why I'm making such a big deal out of availability zones. Availability zones, as their name implies, are key tools for building highly available applications. If you partition your application across availability zones, you can better isolate from any issues. And what do I mean by issues? Well, as you're going to see, we've designed a large amount of redundancy into our region builds. But even with that redundancy, we live on planet Earth. And on planet Earth, anything can fail. Tornadoes can happen, asteroids can potentially hit, lightning can strike. There are many problems that can happen that no amount of redundancy can protect you from. And so for that reason, If you partition your application across availability zones, you can achieve extremely high availability. And so this was one of the first features that we launched after launching the EC2 service. It's been a key building block of Amazon's reliability over the years, and we were excited to share it with customers, and we still are today. Okay, let's go back to our anatomy. We've got our availability zones. We now connect these availability zones with fully redundant, isolated metro fiber once again. This provides high throughput, low latency working to and from each of these availability zones. This makes it as easy as possible to run partitions of your applications across multiple distinct infrastructure segments. Okay, now we've got a region. It doesn't do much good if we don't plug it in. So let's connect it to the rest of the world. Each region has 2 independent transit centers. These are fully redundant transit centers that are highly peered and connected to other global networks. And each is redundantly connected to every availability zone in the region through multiple redundant metro fiber connections. So, as I mentioned, and as you can see, we have a lot of redundancy built into AWS regions. We will do everything we can to make sure that you never see a failure. And if you use availability zones, you can achieve even higher availability. Now let's look at the networking supporting our global infrastructure. Here's the map of the launched regions once again. Now, let's go ahead and add in our points of presence, or POPs. These are the highly connected edge locations that we use for CloudFront and AWS uses to peer with the eyeball networks all across the world. Today we have over 100 points of presence across the world, and these too are expanding rapidly. Now here's how it's all connected. All of these regions and all of these POPs are connected by the Amazon Global Network. The Amazon Global Network provides private connectivity between each of these locations with a highly redundant network. What you see pictured here are the major links in that network. Each of these links is one or more 100 gig connections. And in most cases, there are many connections. This is a great story once you're all in AWS. But how do you connect in? What if you need to connect back to your data center? That's where Direct Connect comes in. AWS Direct Connect makes it easy to establish a dedicated network connection directly to AWS. You can see I've added the 67 Direct Connect locations represented by blue dots. This is where we can meet your network, and you can peer with us directly. And again, we're expanding this footprint rapidly. And we've recently launched a new feature with Direct Connect, Inter-Region Direct Connect. This means that customers can now establish a connection with any of these 67 Direct Connect locations and securely connect via our private backbone to any AWS region. Okay, so that is my high-level overview of our infrastructure. As I said, we're just getting started, and I fully anticipate that in future updates, this map will continue to grow and continue to get more connected. Now, I want to move on to one of the big meaty sections for tonight. Our goal, my goal, is to give you a little glimpse under the cover at some of the things we're doing. And we're also going to talk to you about how we innovate at scale. And so our first topic for the evening is going to be computing at scale. Now, I have a little sweet spot in my heart for compute. My first role at AWS was as the general manager of EC2. And I got to launch that service and shepherd it through its first few years. And man, that was a wild ride. But it has come such a very, very, very long way. And some of that story we're going to tell you here tonight. So, the chart behind me shows the growth of what I would call standard cores for our external EC2 business. These are your normal x86 processor cores that are running in all of your instances. You can see that things are growing at a very healthy clip year over year. While that's pretty impressive growth, let's look at what we call accelerated compute. This graph shows the growth of GPU and FPGA cores. This is exponential growth. and it's being fueled by a sea change in computing. Customers are using new types of computing in innovative ways, and it's very exciting to be part of enabling this change. At this time, I'm excited to introduce Dr. Matt Wood, GM of Artificial Intelligence at AWS. He's going to come up and share some details about how customers are using accelerated compute, including the new P3 instance.
Thank you, Peter, and good evening, everyone. Welcome to reInvent. So as Peter was saying, machine learning is undergoing something of a renaissance at the moment. It seems like machine learning comes into the forefront of our minds every 4 or 5 years, but it's never really stuck before. And the reason for that is that it's almost always been constrained because of scale. But today, with the cloud, we're able to address these challenges of scale. We're able to amass the amount of data that we need, store, analyze, and then train models on it in hundreds, if not thousands, of GPUs, and then run inference and prediction against those trained models at enormous scale, at low latency in production applications. And it's been incredibly exciting over the past year or so to watch multiple applications be deployed onto AWS that are really pushing the forefront of machine learning in the real world. I'd like to tell you just about a couple of them right now. Too Simple is a startup company based over in Beijing and in San Francisco. And they recently completed, in the real world, a 200-mile fully autonomous drive of this truck. The truck used cameras as its primary mechanism of orienting itself in the world. And it moved safely those 200 miles from San Diego to Yuma in Arizona. And this is what they call a level 4 drive. That means that there was a human driver behind the steering wheel, but the car was able to move safely in almost all environments. And when it knows that it's not capable, it flashes up a warning, and the human driver takes over. That's just one step away from the gold standard, level 5, where there is no steering wheel, no brake, and no accelerator, and no human in control. And this is running today live in the real world. Another example, medical imaging. A company called Matrix Analytics runs deep learning on AWS in order to be able to identify tumors on CT scans. So this is a sagittal section through a chest, and you can see there in the bottom left-hand corner a highlighted nodule. And that nodule has a high risk of becoming cancerous. So these sorts of deep learning systems are able to not just help radiographers and physicians identify tumors more early, but they're also able to be routinely run against any chest X-ray. And that means that at any time, as a secondary diagnosis, we're able to identify nodes and nodules on lungs earlier. And the earlier you can detect these nodules, the quicker that you can cure them. And it's advances like this that are leading to a significant improvement in patient outcomes because they can be routinely applied to every single CT scan that's taken in the world. Finally, Clemson University, one of my favorites. Talk about scale. Clemson University were running a natural language processing algorithm. And they wanted to do an enumerative search of all the parameters that were going to process and automatically categorize 500,000 journal articles. And for this, they needed a lot of compute. And so using Spot on EC2, in just 2 hours, they were able to provision 1.1 million cores in order to be able to run this. Enormous amount of compute. When we talk about scale, this is what's capable today. And this sort of volume, this sort of scale would have been simply unimaginable even 10 years ago. And today, it's pushing the forefronts of machine learning. So what we've seen probably in the past 12 to 18 months are really 3 quantum leaps forward in terms of the infrastructure that is driving machine learning into the real world. I'm going to run through these 3 with you now. The first is hardware acceleration for machine learning. This took a dramatic quantum leap forward with the introduction just last month of the NVIDIA V100, codename Volta. This is a deep learning beast. Not only is it one of the largest pieces of silicon I've ever seen in my life, but it was built from the ground up to accelerate in that silicon deep learning. Now, deep learning is a tool which has really come to the forefront in the last couple of years as being able to solve some of the hardest challenges in computer science. any system that requires human-level intelligence, whether it's voice, natural language, understanding, vision, these are all powered by deep learning. And it's Volta which has provided a significant acceleration in the way that you can train and infer predictions against those deep learning models. So by the numbers, we introduced Volta in the P3 instance, the largest of which we call the P3 16 extra large. Just sounds so meaty. This has 8 Tesla V100 GPUs inside it. We provide 128 gigabytes of GPU memory. That allows you to build very sophisticated, large-scale models. There are 40,960 CUDA cores inside the P3 16XL. And this is incredibly important because deep learning can be accelerated and can be parallelized extremely easily. The easier and the faster and the more that you can parallelize it, the quicker your training jobs run. In addition to that, NVIDIA introduced the Tensor Core, of which there's over 5,000 on the Volta chip. And these can be connected together at over 300 gigabytes per second. That means that you can transfer the weights of your model, and you can parallelize not just on a single chip, but across GPUs and even across instances. So let's take a look at the impact that this has. So the hardware acceleration is powered through a deceptively simple inner loop of deep learning. All it is a 4x4 matrix multiplication, which happens over and over again, the results of which are added to the previous iteration of the matrix multiplication. And this inner loop spins round and round and round. And the faster that you can spin it, the faster your models are trained. Interestingly, they took the approach of using FP16, so half precision floating point, 16-bit floating point, in order to be able to accelerate it even further. And Volta can mix precisions. So it can use both 16 and 32-bit floating point numbers to gain extra acceleration. So what this means is that on a single P3, you can get over 1,000 teraflops of performance. That's a petaflop in a single instance on EC2 today. So that's the first. The second is that having all this hardware acceleration doesn't make a lot of sense unless you have software and frameworks that can take advantage of it. And in the past couple of months after the introduction of Volta, we've seen significant improvements in machine learning frameworks. These machine learning frameworks put deep learning in the hands of mere mortals. They allow you to very quickly and easily build, train, and deploy deep learning systems. They're traditionally open source. They have strange names like TensorFlow and MXNet and Caffe2. And our approach at AWS is that we want AWS to be the best place to run all of these engines. Whether it's TensorFlow, MXNet, or Caffe, we want all of them to be able to run incredibly efficiently both on EC2 and on Volta. And so we worked very much backwards from what we were hearing from our customers. Our customers were telling us that they wanted better performance out of TensorFlow. And so we took a look at TensorFlow, we applied some patches, we ran a ResNet, which is an image classification neural network, training run on a P2, 8 extra large, and we compared that to the P3. And we saw a significant improvement, 3 to 4x improvement on TensorFlow with P3. We did the same approach with MXNet, and we saw similar improvements when we were running in FP32, using those 32-bit floating points. When we started to make modifications even deeper inside the engine to support the multi-precision, both 16 and 32-bit floating point, we saw an even more dramatic improvement in training performance. 7x or 8x in the case of training a neural network for object classification. So incredible increases in raw training performance. But what's even more interesting, and arguably more important, is the price performance. And when you start to compare the cost that it takes to run a single image through the training process, you can see the differences. So it is 4 times cheaper to be able to run on a Volta box than it is on a P2 box for ResNet 50. All of these engines are available today with a single click. You can jump up onto the AWS Marketplace and you can pull down a pre-configured, pre-optimized army, which has all of these engines ready to go for Volta and for P2. We include the Conda environment, which provides virtualized environments for data scientists. We make a source code army available so you can get into the guts of the engine and make modifications yourself. And also just a clean slate base army with no engines installed so you can start building your own deep learning frameworks. And these run on Amazon Linux and Ubuntu. The third quantum leap is really the rapidly growing community of tools and organizations that are banding together to help developers drive machine learning even further forwards. And we've been lucky to be involved in a couple of these. The first, which we announced 2 months ago, is a new library for machine learning from AWS and Microsoft that we call Gluon. Gluon provides a significantly more friendly approach to machine learning. It allows you to use imperative models, that's what you're used to using with Python, to be able to define dynamic neural networks which you can train without any decrease in training performance. We also worked with a large consortium, including Microsoft again, Facebook, Intel, ARM, and more, on the Open Neural Network Exchange, or ONNX. ONNX provides an open standard for moving trained networks between these different frameworks. We want customers to have the opportunity to be able to train on one engine and then run on another. So this provides interoperability between frameworks, which is important when you're moving between these engines. The third and final example is NNVM and TVM, which is a collaboration between AWS and the University of Washington. Here, we're introducing NNVM, which is a neural network custom compiler, along with TVM, the tensor virtual machine. And together, these two form an abstraction layer so that developers don't have to worry about the underlying hardware on which their neural networks are running. All you do is give the neural network definition to NNVM and TVM, and it will spit out an auto-tuned kernel for the specific hardware that you're running on. It's a dramatic cost saving when you're trying to drain every ounce of performance out of the hardware that you're running your machine learning on so that you can drive your trucks, so you can identify your cancers, and so you can run extraordinarily large natural language processing. And with that, I'd like to hand it back to Peter. Thanks a lot.
All right, thank you, Matt. All right, for our next segment, I want to take you even deeper into computing and give you a peek underneath the covers at the EC2 instance. So many of you may have heard people talking about next generation clouds. This makes no sense to me. The cloud doesn't work that way. The cloud is constantly evolving. The cloud is constantly getting better. You see this externally when we launch new features, improve performance, launch new services, but it's happening underneath the covers as well. And that's the story of the EC2 instance tonight. I want to show you the work we've been doing underneath the covers. Now, the theme of Tuesday Night Live is innovation at scale. And one of the exciting things about scale is that you can make significant investments in every part of your infrastructure. Because you can amortize that investment over such a large installed base, you can make really, really large investments. You can optimize almost every part of your infrastructure. And that's also the story today, because nothing runs at greater scale for us than our EC2 instance fleet. And so we have spent a lot of time optimizing. Let's have a closer look. Okay, I'm going to start with an overview, a very high-level overview of EC2's architecture. We'll start in the middle. At the core of everything in EC2 is a fast, inexpensive, and very reliable network. If you want a really, really reliable network, you build in a lot of redundancy. And you don't do too much in the network. You route packets, you route them fast, and you route them well. Okay, next we add in a set of what I will call management services. These are the services and microservices that manage all sorts of things. Instances, machine images, security groups. These management services interact with the customer via the APIs. And the customer expresses their intent. What do they want their EC2 environment to look like? And then these services are responsible for making that intent into reality. Okay. This brings us to our protagonist of this talk, the EC2 host. This is where the magic happens. This is where customer instances run. And this is where we run what I'm calling EC2 host software. We'll get into more detail in a minute on this, but this is the software that's responsible for making the customer's environment look exactly like they told us to. Now, this picture is pretty much what EC2 looked like when we launched back in 2006. Obviously, a lot has changed. For example, shortly after launch, we added the EBS service. EBS provides automatically replicated and managed block storage. To add EBS, we had to build a service to manage all that storage. You can see that on the lower left of the graph. We also had to add some management services to manage these storage and interact with the EC2 instances to configure it. You'll see those on the right. And we had to extend the EC2 software to present EBS to the customer instances. Of course, we've added lots of other services and features over the last 11 years, but that's not our story tonight. What I want to do is zoom in on our EC2 hosts. As you can see, there's a hypervisor, and it manages resources and presents them to the customer instances. Then there's a bunch of services provided by what I called EC2 host software. At a high level, these services are responsible for managing and securing the EC2 host and providing all the network and storage abstraction that the customer asked us to provide. For example, the networking component translates packets coming to and from the EC2 instance to conform to how the customer configured their network and their instance. And the storage component does a similar set of operations for the customer's configured storage resources, whether local or managed EBS storage. And then the third set of services really provides security and management for the overall EC2 instance. Before we dig into how the EC2 host has evolved, let me briefly touch on some of the key goals we have for EC2 instances relative to the EC2 host. First is security. This is true of everything we do in AWS. Everything starts with security. The EC2 software plays a key role in securing the EC2 instance and the EC2 environment. For example, it mediates all traffic going to and from each and every EC2 instance. It's also how we assure the integrity of our hardware, our firmware, our software, and the customer's images. And it provides valuable visibility into the instance environment for our monitoring. Our second goal is performance. Performance can be measured on lots and lots of different dimensions. There's network performance, there's storage performance, there's CPU performance, and every application cares about different dimensions along every one of those. And it's not just absolute performance that matters. Performance variability matters. Absolutely nothing is worse than seeing something work and then have it stop working. Nothing makes you trust your infrastructure less than when there's variability introduced into it. Finally, we want to provide familiarity. What do I mean by familiarity? We want EC2 instances to look to customers like native hardware abstractions. We want them to feel just like native hardware. We want customers to be able to use EC2 instances exactly the way they use bare metal. A good example is EBS. When we were first launching EBS, we considered using iSCSI, which is a block protocol that can be easily run over the existing network interface. Now, this would have been easier for us, but the problem is it adds a lot of undifferentiated heavy lifting for our customers to manage the iSCSI client. And we want to remove undifferentiated heavy lifting, not add to it. So we implemented EBS as a native block device. Today, your EBS volumes look like NVMe drives. Okay, now that we've looked at the goals, let's get back and look at the evolution of the EC2 host. So again, this is what the EC2 host looked like circa 2011. This was the same slide we looked at earlier. And this brings us to the Nitro system architecture. This was our vision for the future of the EC2 host. The idea is rather straightforward. Rather than run those functions that I just discussed on the server hosting the customer instance, we could move them to specialized hardware. We call this the Nitro system. The Nitro system would be built to be modular, and these functions would be built on microservices on the Nitro system. This would allow us to move quickly and evolve. The benefit of this approach is that we can allocate all the server resources to customer instances. Our goal was to make the EC2 instance completely indistinguishable from bare metal. Now let's walk through the evolution of the Nitro system. Our first deliverable in this journey was the C3 instance. With the C3 instance, we moved the network packet processing functionality that I discussed to the Nitro system. The network packet processing functionality is one of the most resource-intensive operations on the EC2 software. And it's also one of the operations that has the most direct impact on customer performance. Any delay in the packet processing pipeline manifests itself as network latency to our customer instances. So the C3 launched here at reInvent in 2013. And we didn't talk about the Nitro system at the time. What we talked about was the benefit to the customer. So let's look at that. Okay, 3 big benefits for the C3. The first is the specialized Nitro system was able to process network traffic more quickly than even our optimized EC2 server code. As a result, customers saw a 20% improvement in their network bandwidth with the C3 instance, using the same networking fabric. It also resulted in a 50% reduction in network latency. And finally, not only did absolute performance improve, but because there were dedicated resources on the Nitro system, performance variability decreased. The C3 instance was very well received. In fact, it was our fastest growing EC2 instance to that point. Even before we launched the C3 instance, we were working on our next generation Nitro instance, the C4 instance. The goal with the C4 was to move storage processing to the Nitro system. Much like networking, all storage requests from a customer's instance need to be validated and routed to the correct local or remote managed storage, i.e. EBS. And again, much like networking, this is very resource intensive and performance sensitive processing. The C4 instance was launched 1 year after the C3 instance, again here at reInvent in 2014. Let's look at the results of the C4. The first big change with the C4 is that it was EBS optimized by default. Now I'm guessing many of you don't remember EBS optimized options on EC2 instances, and that's a good thing. Before the C4 instance, customers wanting the highest performance with their EBS volumes could tell us to EBS optimize their instance at launch time. And this was a clue for us to partition the resources on the server to assure that they had great EBS performance. But this was a pain for customers and, frankly, complex for us. With the C4, this was no longer necessary. All instances have dedicated resources on the Nitro system to process their storage requests. And all instances are therefore EBS optimized by default. And so EBS optimized falls into the annals of history with the C4. Also, because we've offloaded all this storage processing, we were able to give back about 12% more system resources to customer instances. Okay, so things moved very quickly with the C3 and the C4. The results and the customer enthusiasm about the performance increased our conviction on the Nitro path. But to get to our next milestone, we had a big decision to make. Up to this point, the Nitro system was purpose-built hardware, but it utilized commercially available ASICs, or silicon chips. Our initial Nitro instance took advantage of components that were commonly used in network devices. And our second generation Nitro system used a ASIC from a startup called Annapurna Labs, which allowed us to easily create NVMe devices, hence offload our storage. But this approach was working well. But to get to the true long-term vision of Nitro, we knew we had to think differently. Our first option at this point was to stay the course. We could continue to try to find the functionality we needed with commercially available parts. But we needed specialized capabilities at this point, specific to EC2. Not only that, while we were able to find the functionality we needed so far in commercially available ASICs, we knew that we were buying features and functionalities that we didn't need. And this was adding to the cost structure of every EC2 instance. So our second option was FPGAs, field programmable gate arrays. Now this is really programmable silicon. Super cool, and we've actually got an FPGA instance in EC2, and I had thought about doing a deep dive here on that tonight, but we don't have time. FPGAs are very cool, but for our application, they didn't quite work. Now, we could use FPGAs to fill in the white space from what was missing from the commercial silicon available to us. But FPGAs have drawbacks. The biggest one is cost. While FPGAs have lower upfront costs than silicon ASICs, they have a significantly higher per-part cost. And at EC2 scale, this would again mean a lot of additional wasted cost. So, certainly, one of the most extreme ways to optimize something is to build custom silicon. Building your own ASIC requires tens or hundreds of millions of dollars. It requires a specialized team, and it requires years of work. You need to be really sure that you have a problem that merits this investment and the scale to merit the investment before you go down that path. Our choice was to pursue the functionality we wanted at the lowest possible cost, and so we chose to pursue a custom Nitro ASIC. But how? As I mentioned, we had worked with an innovative company called Annapurna Labs in creating our second-generation Nitro system. Not only were we impressed by the Annapurna technology, but we were impressed by the Annapurna Labs team. The team was uniquely talented and missionary in their approach, and they felt Amazonian to us since the first interaction. And they shared our passion for combining silicon innovation with the AWS cloud. So, in early 2015, Annapurna was acquired and became part of the AWS team. We immediately started working with them on our next generation ASIC that incorporated both teams' ideas and learnings. This brings us to now. We made the C5 instance generally available earlier this month. C5 represents the culmination of years of work on EC2 host software and Annapurna silicon. The C5 makes use of all the capabilities of the first Annapurna silicon developed since the team joined AWS, and it debuts the Nitro hypervisor, which was designed from the ground up to work with the Nitro system. Let's look at each of these. First, the new EC2 hypervisor. The Nitro hypervisor is based on the core KVM technology that's part of the Linux kernel. But don't jump to conclusions. This isn't your standard off-the-shelf KVM that ships with your favorite Linux distribution. We actually use a fairly small amount of the KVM technology, just the core parts that come with the Linux kernel. Mostly, when people talk about KVM, they refer to a deep stack that does a lot of virtualization. But as you've seen, in our environment, those components live on the Nitro system. This brings us to the second big change with the C5. As I mentioned, this is the first instance to take advantage of all the capabilities of the first post-acquisition Annapurna silicon. This ASIC was designed to provide specific functionality needed by the Nitro hypervisor and the EC2 software to allow us to completely offload the EC2 software to the Nitro system. And so what are the advantages of that? Well, first, nearly 100% of the available resources can now be allocated to customer instances. This is a big deal because it means that we can produce instances that whose performance is indistinguishable from bare metal hosts, possibly even better. The second benefit is that we can do unique and innovative things to further assure the security of the EC2 host and the customer instance. The Nitro system gives us a secure root of control to run our software on, which is separate from the server that hosts the customer instances. Now, I'm not going to be able to do this subject justice here tonight, but at the end of this talk, I will point you to some sessions that will go much deeper for those of you that are interested. I think it's a very interesting topic, and I highly recommend you go. Another part of the story is the VMware Cloud on AWS. This is a very exciting development for our joint customers because it gives VMware customers the ability to take advantage of AWS while leveraging what they already know and what they already own. These customers can use their existing skills, tools, investments, and operational practices and get the cost elasticity and breadth of functionality of AWS. But to make this work, to make this really work, we needed VMware ESXi to run directly on EC2 servers. And that is exactly what is happening. Because all of the EC2 software lives on the Nitro system, ESXi can run natively on the EC2 host. So now this brings us to the most exciting part of our story. What's next? Is everyone still with me? Good. Awesome. So, tonight, I'm pleased to announce EC2 bare metal instances. These new bare metal instances give customers and partners the best of both worlds. You get direct access to underlying hardware with the elasticity, security, and scalability of the AWS cloud. So what are the benefits of bare metal? Well, now virtualized, non-virtualized workloads that need a specific hypervisor or access to specific hardware features, and workloads with restrictive customer hostile licensing can take full advantage of the benefits of the AWS cloud. And once these workloads are in AWS, they can take full advantage of other AWS services, including virtual private cloud, elastic block store, elastic load balancing. Several customers and partners are already hard at work building cool things with EC2 bare metal instances. As I mentioned, VMware Cloud on AWS is built on EC2 bare metal instances. These are available initially in private preview, or public preview, as i3 bare metal instances. But we will be rolling out additional instance families over the coming months. Now, this story doesn't end here tonight. I have now, here in my pocket, hot off the fabs, our next generation ASIC, EC2 Nitro ASIC. There's literally twice as many transistors on this ASIC than our previous generation. Now, these are literally just started arriving as engineering samples to our teams. And we're hard at work building instances and features, which we look forward to talking to you about in the future. But we're not done. So why are we investing so heavily in EC2 instance performance? It's because our customers need performance. And they're doing some really, really cool things with high-performance EC2 instances. One of those customers is Autodesk. They're doing lots of cool things on AWS, and one of the coolest, in my opinion, is called generative design. So I'd like to bring up Brian Matthews, Vice President of Platform Engineering at Autodesk, to talk about how they're using AWS. I think this will give you a completely different perspective on innovation at scale.
You probably know that there's over 7 billion people on Earth today. But you might not know that the global middle class is growing faster now than at any time in history. In fact, there's over 400,000 people who will join the middle class today and every day into the future. That's 160 million people every year who are going to want their refrigerators, their cell phones, and their washing machines. We're going to need to build 14 million buildings by the year 2050. That's 1,000 buildings per day every day for 33 years just to keep up. 10 billion people are going to need their highways, their hospitals, their education and energy, their water and wheat. But there's a problem. Current methods for building the world around us are running into environmental, social, economic, and resource constraints. In fact, 30% of all construction spend is waste, often due to bad planning. After all, each building that you see and live in are often just the beta release. So if we're going to imagine, design, and create a better world, we're going to need to innovate. We need to do more, better, and with less. Now, I work for a software company called Autodesk, and we make tools for people who make things. It's our customers who are the ones that build all the buildings in the world, the smartphones that you use, the bridges that you drive over, and the movies that entertain you. And our software tools allow people to test their ideas virtually, simulate the real world in a virtual space before you bring it into the physical world. So our customers are the ones that simulate stress and strain, like on these mechanical parts. Or fluids, when engineers are studying things like aerodynamics. Some of our customers even simulate light. Many of the movies that you watch are actually simulations of billions of photons of light bouncing around in a virtual scene made out of millions of surfaces on their way to a virtual camera. It can take hundreds of thousands of cores to render a normal movie these days. Now, simulation is a really powerful tool, but there's a problem. Every time you increase the resolution of a simulation, every time you double the resolution, the amount of compute power required goes up by a factor of 8. We are talking about an order n cubed problem here, and that's really not a fun place to be. These simulations can take hours or often days. So let's take a car seat, for example. We want it to be light for fuel economy, but we want it to be strong enough to save our lives. Imagine we had just one variable to optimize, the thickness of the metal. If we make it too thin, we die. We make it too thick, and we waste fuel. So what is the optimal choice between these two constraints? Well, before the cloud, simulation was like a game of Battleship, right? You figure out your initial guess at the thickness for the metal. It's like E6. You wait 3 hours for the simulation to come back and tell you, miss. So let's make the metal a little thicker. Wait another 3 hours, miss. By the time you get a hit, you're willing to settle for any acceptable solution rather than having the patience to find the optimal solution. This process does not scale. And that is where AWS comes in. You see, in the same time that it takes to do one simulation on one computer, in the cloud, we can scale it up. We can run 100 variations of this part on 100 servers in the same 3 hours, and something new emerges. The computers become our design partner. Instead of just validating our design, it is now telling us it has found what the optimal design is. But that's just level 1 of using the cloud for simulation, because we only had one variable, and we could use a brute force approach. But of course, real design problems have many variables. We can't use a brute force approach. We need to level up. Now, Lightning Motorcycles is an Autodesk customer. They make the world's fastest production motorcycle. Oh, and it just happens to be electric. Now, the thing about being a winner is you want to stay a winner. And Lightning came to us wanting to make this part lighter, the swing arm. It has a tremendous amount of force on it, and so it's a heavy part on the bike. It impedes the performance. It's a complex problem because there's almost an infinite number of ways that we could potentially remove material from this part. We can't try every possibility. So instead, we used a process called generative design. Now, as before, a human provides an initial starting point. The cloud on many parallel computers do many different simulations, sometimes removing a little material here, a little material there. Some simulations find out they actually have to add some material back. It gives a surprising organic result, but it's lighter and it's stronger. In many ways, generative design mimics evolution. Rather than a population of competing organisms, what we have here is a virtual population of competing parts in a simulation. One of these here is an actual cat pelvis, one is a dog pelvis, and one is a motorcycle swing arm. At level 2, something new emerged again. When we up the scale, we now have synthetic evolution. So let's look at level 3. In this case, rather than provide an initial design, we're only going to provide the constraints. Where does the part attach to the bike? What are the forces involved? And what kind of materials are we willing to use in the manufacturing process? The cloud isn't just converging on a solution from our design. We didn't give it a design. It is divergently thinking. It is exploring creatively the possible design space. And this is where the human imparts our values into the process. See, we have to make judgments between potential optimal solutions. How do we want to make the trade-off between things like safety versus cost, or weight versus environmental impact? Once we've chosen a design, we can use AWS again to help optimize its manufacture. What's the best way to print? How can we use machining to finish the part? The result is something amazing, surprising actually. The cloud has produced something beyond organic. It's like playing evolution forward a few million years in an afternoon. Now, aircrafts are some of the most highly optimized machines that we make. They have to provide safety at low weight. It's a hard design problem. We worked with Airbus to lightweight this part, the bulkhead of their latest A320 aircraft. It's an already highly engineered part for lightweight and safety. Again, we used generative design, this time with an algorithm that was inspired by the growth patterns of an organism called Fusarium polycephalum. And try saying that fast in front of a lot of people. Autodesk software, powered by AWS, came up with 10,000 solutions. Each met the requirements, but with different trade-offs. Now, in an industry where a 5% weight reduction is considered a huge deal, this part is an astonishing 45% lighter. And here's the thing, it's actually stronger than the part that it replaces. Now, if applied to the entire fleet of A320s, Airbus estimates that the fuel savings would be equivalent to removing 96,000 vehicles from the road. Imagine the environmental impact. And imagine applying generative design not just to that part, but many other critical parts, such as the hundreds of seat supports. And what if we applied generative design to the entire aircraft? Wouldn't that make flying fun again? Doing more, better, and with less is possible when you reimagine things with the cloud at scale. But so far, we have only looked at physical goods. Let's think back to that 1,000 buildings a day that we're going to need to build. You know, architects really haven't had the choice or the option to consider all of the ramifications and trade-offs of every design decision that they make. And they certainly couldn't ponder the needs and whims of all of the inhabitants. But the cloud can. For Autodesk's latest office building, we used generative design, and we had the usual goals around cost and space and environmental impact, and we simulated everything. We did light, scenic views, travel paths, energy efficiency, and many more. But we also surveyed the inhabitants. Who do you have meetings with? How bothered by noise are you? How often do you get coffee? We incorporated everyone's input and brought it into this design. Imagine scaling this approach to entire cities. Generative design lets us look deeper into our design problems, helping us make better choices. So let's level up again. Everyone's talking about machine learning. And if you're listening, you also know that you need a lot of training data to make machine learning effective. Now, if you're Amazon or Google or Facebook, you've got a lot of data, and that's great. But if you're a startup, well, good luck. Any of you remember this video game, Breakout? Not old enough? I am. It was the original video game. I used to stay up all night learning to master this. Now, in the cloud, we can teach a computer to play in a simulation. It can randomly move the paddle back and forth, and it'll notice that sometimes, with some movements, it gets a higher score, and sometimes it doesn't. It's learning. It's synthetic training data being generated by the cloud, but it's a slow process. But of course, the cloud allows us to scale it. And so overnight, a computer in the cloud with many parallel machines generating synthetic training data can become the world master champion at Breakout. And unlike when you try and teach your friend here how to play, when the cloud learns Breakout, all computers have learned to master Breakout. Now, with traditional robots, absolute conformity and precision is required. If any of these machines is out of calibration, well, the entire production line will grind to a halt. Wouldn't it be great if we could stop having to conform the world to the needs of our machines and instead have the machines adapt to us and to the world as it is? Automating a simple task of trying to pick a part out of a bucket requires an army of software engineers. But at Autodesk, we created virtual robots with virtual parts, a virtual camera, virtual light, virtual shadows, virtual physics, and we ran a simulation in the cloud, in parallel, on many machines, doing random things, generating synthetic training data. The cloud lets us scale. And we've applied this in the real world with the 3D printing using robotic welding. The thing about welding is that molten metal flows in random ways, and the robot sees that randomness and adapts its approach to get the desired outcome. But we didn't write any code to do this. The machine learned how to do this using synthetic training data of synthetic robots in the cloud, and then could translate that into the real world. So, Autodesk's mission is to imagine, design, and create a better world. And AWS has been a really great partner with that mission. They've allowed us to focus on simulation and generative design rather than on managing storage and databases. And Amazon has continually been updating their game as well, bringing down the cost of computing, and as we saw today with that P3 instance, bringing the horsepower that we need for this new future. After today, if anything, I hope you'll see the cloud differently. The cloud isn't just about moving computers from on-premise to some provider. It's an opportunity to reimagine what you're really trying to accomplish. Every time we increase the scale of computing, a new phenomenon emerges, from optimization to biology-inspired evolution, to creative exploration, to synthetic learning. With generative design, the computer is becoming our partner, almost an empathic collaborator. Yes, it's still just a tool, but unlike the microscope and the telescope that let us see the world as it is, the cloud lets us see the worlds that could be. It's up to us to make the choices. If design is the process about envisioning a better future, how will you use the cloud to make a better world? Thank you.
Thank you, Brian. Generative design is extraordinarily cool, isn't it? Now, my second disappointing news for the night is originally I was hoping to race Werner on his Harley, and I would get one of Brian's cool bikes, and we'd go down, but unfortunately that didn't work out either for logistical reasons. So I'm 0 for 2 tonight, but see what we can do. All right, let's move on to our second little deep dive tonight. I want to talk to you about load balancing. Why load balancing? Well, load balancing is a fundamental building block for high-scale, high-availability applications. And as you might imagine, operating one of the largest websites in the world for over 20 years, and operating the largest cloud computing platform for over a decade, we have lots and lots of experience with load balancing. Some of it good, some of it painful, but all of it important. So here's a picture of our first load balancer, or at least a close approximation. I couldn't get an exact picture of our exact device, but this is pretty close. This was a mean piece of gear for its day. It had a 166 megahertz Pentium Pro processor, 32 megabytes of RAM. That's right. It could scale up to 16 ports. Those could be either 10 or 100 megabits. And it supported high availability, which was really its killer feature. Now, it turns out it supported high availability through a proprietary connector. And you can see that on the right-hand side. It kind of looks like an old parallel port. But you'd lace two of these devices together, and you could have a master and a failover. Oh yeah, and it optionally came with a floppy disk drive. Now, you remember those? These were the new, modern, fangled 3.5-inch floppy drives, not the old school 5 1/4. So, really cool piece of gear. All right, as much as I poked fun at the load balancer in the previous slide, this ushered in a golden age for us. Load balancing made it easy to achieve reliability, scalability, and agility. And that last point is important, and I think it's often overlooked with load balancers. Load balancers allow you to move quickly and optimize later. You optimize only when your costs scale to the point where it's worth optimizing. Small services with light usage have correspondingly small costs. As services grow and costs grow, it's worth investing the time and distraction to optimize. So as I said, this was a golden age for load balancers. There were more providers, faster feeds and speeds, more features, and cost was going down. Things were good, but it wasn't all good. Load balancers were decreasing in price, but they were far from what I would call a commodity. When you want to be a low-cost operator, which is something that has always been in our DNA at Amazon, you have to pay particular attention when part of your infrastructure or your costs start growing disproportionately to the rest of your costs. And that's what was happening with load balancers. They were becoming a bigger percentage of our overall infrastructure spend. Additionally, there were a few technical and operational challenges. Let me highlight a couple. The first of these problems is that hardware load balancers are black boxes. Black boxes are things that you need to operate for yourselves, but you don't get to know everything that's inside. And this is one of the biggest problems with the old world infrastructure delivery model. If you're not the one operating something, it's hard to know what you might need to monitor. And if you're not the one building something, it's hard to know where things might break. This is fundamentally different than a service delivery model, where you have to operate everything you build. I can give you lots of examples, but all of the problems with black boxes kind of have a similar plot. The box usually has some internal resource that has an unknown limit. And because nobody else has ever hit that limit, the provider of the black box doesn't give you visibility into that limit. You don't know if you're days, hours, minutes away from a cliff. You get to know there's a cliff when you fall off. Now, because of this fundamental problem with black boxes, you get smart, and you start using your black boxes in a very specific way. I like to say you stay in the middle of the road. And what I mean by that is you try really hard to use your black box in the same way that everybody else is using the black box. That way, you know that if there's any problems, maybe somebody else discovered them before you did. Now, if you're moving fast, innovating, and building one of the largest fleets of services in the world, it's really hard to stay in the middle of the road. Finally, when you do encounter a problem with a black box, it can be really, really hard to find and fix root cause. And this is because of the inherent information wall between the people that build the black box and the people that operate the black box. Neither side means anything wrong, but neither side can easily share information with the other. The builders of the black box aren't going to share their source code with you. And you, as the operator of the black box, cannot easily share your monitoring and configuration information and everything about your environment with the builder of the black box, assuming they even want to know all those details. So this makes it painful and time-consuming to find and fix issues. The second problem with load balancers is managing all those load balancers. Now, every service you operate needs to have at least one virtual IP, or VIP, or endpoint. And as I kind of alluded to earlier, it should probably have more than one. You should probably have several partitions of your service and use something like DNS to spray load over those partitions. And ideally, each of those partitions would be running in an availability zone. Now, every one of those VIPs needs to be configured on a load balancer. And it also needs to be configured on a failover load balancer. And every one of those load balancers needs to be operated and managed and capacity managed. Now, this may not seem like a big problem, and it's not at small scale. But at large scale, this can become a tiresome burden and a real problem. So at Amazon, we don't do things small very well. At Amazon, we got the service bug early. I think we were doing microservices before we had a name for them. To give you some perspective, 10 years ago, we had 6,000 virtual IPs or endpoints at Amazon. Now, how many do you think we have today? 600,000. Now, I don't want to configure all those load balancers. The challenges I highlighted and this massive scale has driven us to invest heavily in load balancing over the years. One of the biggest investments we made in load balancing was for Amazon S3. The massive scale and success of Amazon S3 drove us to need an order of magnitude increase in the load balancing capacity. It also incented us to want to lower cost and improve performance. In 2011, we started working on the S3 load balancer. There are a lot of cool inventions in the S3 load balancer. But let me highlight a couple tonight. First of all, you can see pictured a very early generation of the S3 load balancer. And you'll immediately notice some things about it. It's not a hardware appliance. It's not a gussied up server. It's not a big blade server. It's a full rack of networking gear and commodity servers. The other big difference between this massive disaggregated load balancer and a traditional appliance-based load balancer is that the S3 load balancer operates like a distributed system rather than a highly available appliance. Let's quickly look at that difference. Here's a classic load balancer configuration. We have two black box appliances supporting one or more VIPs. The device on the left is the primary load balancer, and the device on the right is the failover load balancer. The requests arrive to the device, the master, the device on the left. It likely shares some state with a device-specific proprietary protocol. At least it's not a specialized cable anymore, but it's still a proprietary cable, or a proprietary protocol. Now, the second problem with this drawing is this is a 2N architecture. And 2N architectures have some inherent problems. First, you have to reserve enough capacity on the failover device to deal with a failure. So that means that these two devices, at best, can run at 50% utilization. Now, they're likely going to run at much lower utilization because you have to save capacity for things like traffic variations. But 50% is your best case scenario. The second problem with a 2N setup is a single failure puts you one failure away from customer impact. And as an operator, I can tell you I don't sleep well at night when I'm one failure away from customer impact. So, 2 is a terrible number for high availability. Let's look at the S3 load balancer. Okay, here's our S3 load balancers. Connections arrive at the load balancer, and the switch at the top of the rack that you saw earlier routes those requests to any one of the hosts in the rack. It doesn't matter which host, because any host can handle any traffic. This is super simple. Now, when traffic is routed to a host, it either knows what to do with the request, or it uses a set of distributed systems algorithms to find out what it should do. The same sorts of algorithms we use in services like S3 to propagate data. I won't go into the details here, but you can think of things like, you can think of these as distributed systems algorithms. But the key point here is that rather than storing state on 2 devices, state is replicated over many devices. These sorts of systems are much easier to operate because hosts can fail and data is re-replicated transparently. They can also run at much higher utilization because this is an N+1 architecture. So this device can run at 80, 90% capacity depending on how you've got it configured. Very different than a 2N architecture. We've been really, really happy with the results we've gotten from the S3 load balancer. It's handled some truly amazing traffic. The portion of S3's traffic handled by the current generation of S3 load balancer in a single region, and remember, this is just a portion of the total S3 traffic in one region, is 37 terabytes per second. Terabits per second, I'm sorry. Now, that's a load balancer. So, as I said, we were delighted with the success of the S3 load balancer. We addressed several of the challenges that I talked to you about earlier. Most importantly, cost. And the results have been that we've been able to continue to scale and optimize S3 performance. But we still had work to do. First, while this was no longer a hardware load balancer, we still had a dedicated load balancing rack. And because of this, we needed to manage load balancer capacity separately. Secondly, while S3 uses many S3 load balancers per region, most services, almost all services, only need a tiny little sliver of a single S3 load balancer. And third, as you might have guessed, because we were building this as the S3 load balancer, we optimized it for S3. So we went about turning the S3 load balancer into a product. And that product we call internally AWS Hyperplane. Now, be careful, this is an internal service. So why am I talking to you about an internal service? Well, I'm telling you about this service because it underpins many of the AWS services that you likely use today. Let's look at those. There are 4 services which are currently exposing functionality that's built on AWS Hyperplane, and I suspect there'll be more to come. The first is the Amazon Elastic File System, or EFS. The second is Amazon Managed NAT. The third is our network load balancer, and the fourth is Private Link. Let me walk through each of these quickly. Amazon Elastic File System is a fully managed, POSIX-compliant file system. It can be used with any NFS client, and it scales up to petabytes of storage, tens of thousands of instances with concurrent access, and gigabytes of throughput. We use Hyperplane to help provide this highly available, highly elastic service. Think about how different this use case is from your typical HTTP server. Again, you're using an opaque NFS client, and these connections are stateful and extraordinarily long-lived. Connections to a file system can last days, months, or even years. EFS is in production for a couple years, and all that time, it has been utilizing Hyperplane under the covers. Okay, let's talk about Managed NAT. Managed NAT allows customers to create a NAT gateway in their VPC. Instances in VPCs that do not have public IP addresses can connect to external addresses using temporary addresses and ports allocated by the NAT gateway. This is a great feature for VPC users that don't want to put public IP addresses on their instances or accept incoming connections from the internet. A great security feature. And it requires managing a whole host of different types of traffic because customers use all sorts of different things on the internet. All of this traffic has been flowing over Hyperplane since we launched. Okay, this brings me to Network Load Balancer. This is Hyperplane for AWS users. We launched this a couple months ago in September. And now you too can build highly scalable applications using Hyperplane by making use of this Network Load Balancer. The Network Load Balancer provides TCP load balancing. It provides tremendous elasticity and lets your application scale to millions of requests per second. It's also very fast. In fact, it's almost indistinguishable from communicating directly between two instances. It's order tens of microseconds of latency. There are several sessions about the Network Load Balancer here this year, and I'll recommend a couple at the end. But this is a very valuable tool for building highly scalable, highly available applications in AWS. Hyperplane also powers AWS Private Link. AWS Private Link was announced earlier today by Terry Wise, and it allows customers and partners to build and access private services without exposing them to the internet. With Private Link, you can build your service in a private subnet inside of a VPC. Then you can share your service with other VPCs, either in your account or in other customers' accounts. And you can do that without sharing network IPs, whitelisting IPs, configuring firewalls, or even allowing any internet access at all to your VPC. It provides an easy, secure mechanism for sharing services. One of the most exciting things about Private Link is that it allows APN partners to more simply and more securely provide services to other AWS customers. We are really excited to be able to enable the ecosystem with such a powerful tool. And so that's how we do load balancing at AWS scale. Another area where scale is really important and allows us to innovate is security. And now I know I told you that everything at AWS starts with security, but tonight it's also going to end with security. So I'm very excited to invite Steve Schmidt, VP and Chief Information Security Officer, to come up and discuss how we think about security and innovation at scale.
Good evening, everyone. You know what I love most about Tuesday Night Live? I get to announce a new security service, which will make our evening. But first, we get to talk about security at scale. Now, scale drives changes in organizations. It changes how organizations build, how they operate, and security is really no different when you think about it. We require investments in tooling to help us scale as we grow bigger and as we grow at higher velocity. Scale in data requires us to build tools as well to help improve the signal-to-noise ratio, to ensure that we're focusing our most valuable asset, our human beings, on those things that matter most to securing our infrastructure. Because if you don't, they'll drown in the data. Another interesting point is scale allows you to develop best practices. Practices emerge because of their quality, and you can focus on them by analyzing that which works and that which doesn't, much like Matt Wood talked about earlier with analyzing many, many different opportunities in the machine learning space. Think about it this way. Most security errors are caused by misconfiguration. What's the best way to handle those? Tooling. Now, this is my personal tenet. It's a thing that I believe very strongly in. It's something that I think we should all focus on as security professionals. Let's face it, if you keep the humans away from the data, there are fewer chances for problems. And how do you do that? Let's take a step back. At Amazon, we love mechanisms. They drive repeatable, correct behavior. So for example, our CEO, Andy Jassy, has a weekly meeting with Peter, with me, with the other senior vice presidents in the company to go over security issues. That mechanism enforces a culture of observing security as one of the most important things we can do every day. It shows everybody that that's what we have to do when we wake up in the morning and when we go to bed at night. I have a weekly application security business review with my team where I go over all the new services that we're launching and all the new features that we're rolling out. For an example, that AppSec team did almost 1,900 security reviews on services this year. We have to keep up with the velocity of launches that the company has as a whole. Now, the biggest needle mover for us as an organization, however, has been something called security expectations, where we set out goals to every service team, every VP in the company, that tell them how they should be practicing security, and we measure them against those goals. One of them, by the way, is that everybody has to run Amazon Inspector on all of their EC2 instances because it gives us the visibility that we need into the operation of the infrastructure and the correctness of it. Now remember that I said that humans and data don't mix? Well, there is a very important human place in the security puzzle. Contrary to popular belief, developers want to be part of the security solution. They don't want to be part of the problem. The difficulty is they have to get their day job done properly and on time. And it's too easy for security professionals to be the house of no, you can't do that. What we need to be doing is building the tools that give developers the opportunity to make good choices the first time. Additionally, the other side of that scale is our security engineering staff. They're our most valuable security asset because only human beings can make well-reasoned judgments about the very, very gray area of risk in security. And I want those security engineers to have their attention on the multitude of gray areas all the time, the ones that machines cannot reason about. But remember that problem that we had earlier about data and floods of data? It's one of the biggest issues we have to figure out as an organization and as a business, frankly. But this is the fun part, pop quiz. How many security engineers are in the AWS Security Operations Center at any one time? It's a trick question. We don't have one. My personal belief, if you have people sitting in a room looking at screens to make your security detections actionable, you're probably too late. So what the heck? All right, how do we do that? We have a series of on-calls who are responsible for doing security operations across the company, and I'll talk in a moment about how that works. So how many security engineers are performing operations work at AWS on any particular shift? Yep, one, literally. How the heck can that happen? It's all about automation. Now, there is a rotation. The security engineer who's on call, they rotate every 6 hours to the next security engineer who's on call. This happens across 4 locations in the world. It goes from Herndon to Seattle to Sydney to Dublin. That handoff between them is a formal, tool-driven handoff which conveys state, the most important actions, the next follow-ups, etc. There's a primary on-call and a secondary on-call and an escalation path, all driven by tooling. So if the primary on-call doesn't engage on a security issue within the defined SLA, the secondary is automatically paged by the infrastructure. It's not waiting to figure out something happened the next day. If they don't engage, the next in the escalation path is paged, literally up to me. I haven't had one of those happen yet, which is a good thing. But the point there is using the tooling to make the actions happen that you want across the organization. So how does this happen? We find the most common problems across our infrastructure quickly. Literally 5 to 15 minutes is our typical detection interval, and that's mostly limited by the velocity of logs being delivered to our analytics platform. We then take the necessary actions to understand what happens on our infrastructure automatically. We do the forensics and the investigation that's required to understand with precision exactly what's going on in a particular security incident. Again, automatically. not requiring a human being to go capture a disk somewhere. When the individual who caused the problem, maybe a misconfiguration by one of our software development engineers somewhere in the company, they report the problem as fixed back to our trouble ticketing system. And again, we reinvestigate automatically. In most cases, we can close security tickets, internal security tickets, without the intervention of a security engineer. The system can identify the problem has been resolved and resolve the ticket. How do we do that? We use the same tools you have available right now. We use Lambda extensively to drive individual actions. We use event-driven notification to invoke the tools that we used, rather than waiting for a time interval to elapse. At AWS, we've always been really good at giving customers excellent primitives and tools. But you've told us very clearly that bricks are nice, but walls are better, and you want a complete solution. We've built these for ourselves internally, and now we've started externalizing them. Earlier this year, we announced Amazon Macie. Macie is our tool that helps us deal with the incredible richness of data that we possess and the incredible content logs that we have to analyze to understand what's going on. Now, the interesting thing about this is the flood of data is often the biggest downfall of most security analytics platforms, because machine learning is not a panacea for all. But the properly chosen model has to be flexible enough to handle the variety of customers that we have across our infrastructure, and it must be able to evolve faster than our adversaries can evolve. If we don't do this right, the penalty for error is high, and that flood of data that we talked about in the beginning can cause our security engineering staff to drown. So how does Macie do this? Macie helps you understand your data through a classification process. It helps you go through your S3 bucket and understand, do you have personally identifiable information? Are there credit cards or financial transaction records present in your data? Does it contain things like street addresses or zip codes? Or other things that you can configure as uniquely important to your intellectual property or your business? Uses natural language processing to help develop that model for you. Now that's great, awesome, you understand what you have. But the most important part is understanding the use of that information, and that's where the machine learning comes in. It helps you understand exactly how your humans are using the data, whether they're using it from their desk or from their home, what time of day, the frequency of access, and the type of access. Is a salesperson accessing sales-related data, or are they looking at health records, for example? And then cut alarms when appropriate to understand if the access is outside your expected norms. Now, continuous security monitoring is what we all strive for. But doing this at scale without slowing down your business is complex. It's expensive. Traditionally, threat detection requires you to deploy and maintain dedicated security infrastructure, which frankly is hard to automate. It doesn't auto-scale at all, and many existing solutions were designed first for on-premises environments. And frankly, thus they're missing a bunch of additional attack vectors. So building your own requires collection, analysis from multiple sources, developing and maintaining rule sets, building detections, tuning them, incorporating threat intelligence feeds, and it ties up your most valuable asset, your security professionals. So this is why I'm excited to announce Amazon Guard Duty, our new intelligence-driven threat detection service. Amazon Guard Duty is a fully managed continuous security monitoring and threat detection service built for the scale of the cloud. With a single click, literally a single click, you can enable the service. It's removed the complexity of operation that you used to have to go through. No matter what your level of expertise, you can get it functioning on your environment very rapidly. It immediately begins analyzing billions of events from multiple AWS data sources, including CloudTrail and flow logs and DNS logs. It uses an integrated threat intelligence feed from our security engineers, as well as our partners at CrowdStrike and Proofpoint, and identifies anomalies in the operation of your infrastructure and applies machine learning to identify threats with great precision. For example, a compromised EC2 instance that's mining Bitcoin, or an attacker scanning your infrastructure for known application vulnerabilities. It also monitors AWS account access behavior for signs of compromise, such as, is somebody using your credentials to launch an unusual instance type in a geography you've never used before? Most importantly, there's no footprint in your account, no performance impact, no reliability issues with your existing applications or workloads. We operate it completely on our infrastructure. There's no agent to install, no sensor to install, or network appliance for you to deploy or maintain. Just enable the service, and it starts analyzing, raising your security bar across your organization. Customers and partners are always key contributors to developing new services in AWS. And more than 50 customers and partners have been using the service and providing feedback for the past 7 months. All of the partners listed on the slide here have developed integrations, and many are demonstrating those today at the Expo. I encourage you to seek them out and take a look. We're really excited with what they've done. Now, I've talked a lot about the evolution of security over time, on how we've gone from human-powered analysis to automations and analysis, and how scale has driven us to machine learning. So I'm very excited to bring a special person to the stage. She's been one of the founding members of the Amazon Macy service team, Jenny Brinkley.
Thank you, Steve, for the kind introduction. Tuesday Night Live, I am thrilled to be here and talk with you about how we're using machine learning at AWS Security with some of our new services and products and things you'll hear about this week. A quick shout out to the Guard Duty team. Congratulations on the announcement. It's available in the console. Highly recommend that you check it out. As Steve mentioned, I was the co-founder of Amazon Macy. And when we built the service, there really was 3 components that we wanted to think about. How do you protect, how do you secure, and how do you classify content wherever it lives inside of AWS? And to do that, we also worked with some pretty phenomenal partners. Guard Duty and Macy actually both shared a customer as our very first customer to give impact and influence of how we were thinking about workflows and strategies to solve security at scale challenges. So it's my privilege and honor to welcome Greg Peters, Chief Product Officer from Netflix, to have a quick chat with myself and Steve. So let's welcome Greg to the stage. All right, let's get to it. I'm sure everybody also wants to get a quick adult beverage here coming up. So let's just go right at it.
Let's do it.
All right. So Netflix is really known for a few things, being innovative with AWS services, while also open source projects and work. So how does that apply for security?
We're equally as passionate about collaborating with other developers, the industry, and coming up with great tools for security as well. We actually just released a bunch of new projects this year. Brings our total count, I think, of security-related open source projects to around 15.
Awesome.
Most of those are AWS related. They're targeted at tools, applications that security teams can use to deal with high velocity, large scale cloud deployments. It sounds familiar. All while reducing sort of the tax or limiting the tax on developers to get to great security. I think what's been great is we've seen a lot of collaboration. There's a lot of developers out there, a lot of companies out there that want to participate in trying to figure out a new, better way to do security, because you can unlock a whole bunch of new opportunities that being in the public cloud enables.
Awesome. Any projects you can mention specific?
Sure. So actually last DEF CON, we released a couple of projects that allow developers to simulate application DDoS attacks and see how they can deal with that. We've released a couple of projects recently called Aardvark and RepoKit, which take Access Advisor data and use that to automate the setting of application permissions. Those are good examples.
Awesome. That's great, Steve. I mean, open source is so important to us at AWS, so.
It is. So one of the things that we were really proud to announce last year was signal to noise, S2N, which is our version of a TLS library. We thought that the existing options didn't quite meet our needs in terms of performance and security, so we chose to build our own, and we made it available for everybody through the open source process, and we continue to improve it. So for example, we have a FIPS version now that's available to meet certain government requirements in the S2N world. Additionally, we've formally verified the random number generator in the S2N stack. Formal verification gives you the ability to prove the properties of software, that it's actually doing what you expect. And moreover, we've added a few more tweaks into that process, so there's prediction resistance in the random number generator. So even if the random number generator itself is compromised in some way, there's additional entropy that's added back into the process, sort of raising the security bar for everybody for TLS.
That's awesome. So Greg, obviously with the amount of data that Netflix has available, how do you leverage it for security?
Yeah, one of the great things about being the cloud is that we have access to a bunch of well-structured, highly reliable, easy-to-use data sources, and we can use those sources to build automation and tooling around it to support better security. Examples are, at the network level, you have VPC flow logs. You've got at the application service level things like Access Advisor and increasingly CloudTrail. And then we can use that to support a bunch of automation. A good example, thinking back to the open source project we just mentioned, in terms of right-sizing permissions for a new application, that historically might have been done by either being, starting with a super permissive model, which is great for developer speed, but rarely ends up in an optimal security state, or to the other end of the spectrum, a default deny kind of model where you rely on first to sort of bump their head up against a permissions wall and then find the right permission, iteratively go through that process, which is painful and frustrating and slow for a development perspective. So now we get to shift to a totally different approach where developers can just launch a new application, deploy a new application. You start with a wide set of permissions around that, and then we observe how that application actually behaves. And then we iteratively whittle down the permission set until we get to the optimal, aka least privileged, state from a security perspective. But the developer hasn't had to do a single thing. The security team hasn't had to do a single thing. The developer hasn't needed to understand the complexities of a large infrastructure and figure out how to get the right permissions. The security team hasn't needed to know what's specific about that new application, what are the dependencies and requirements for that. It just happens automatically, which is the way to get to great security and the kind of opportunities that we're excited about pursuing.
That's awesome. So you have a few folks from AWS in the audience tonight. What would you like us to work on next? What are some of the challenges that you have that you're like, oh, if I just had this? Like, what would that look like for you?
Yeah, in the security domain, I think there's a set of characteristics which define or at least inform where I think you guys can be way more effective and have an opportunity to produce things that we can't produce. Sure. It's things like where there's a set of data, sources that come from really, wide or disparate sources. Could be across region, could be across accounts. And you need full visibility, super wide visibility to really understand what's going on and identify issues. I think guard duty is a really good example. You guys just announced that. We've been using it for a bit, and it's great for finding things like, hey, we've got an API call using AWS keys that's coming outside of AWS. That might be a signal that we've had a credential compromise or something like that. Another set of characteristics are where there's just a really intensive amount of data processing, right? Where it's difficult or even cost prohibitive for us to go do. Maybe the analytics layer on top of that, the ML, there's a huge investment to get that right. And you guys can amortize the cost of that investment, do it at a way bigger scale because you've got multiple consumers of that product than we could ever justify. Macy's a great example of that. A little bit about that. And it's super effective for us in terms of understanding when there's sensitive data in some of our S3 buckets.
That's awesome. I think the other big piece, and obviously we're really passionate around machine learning and solving and thinking about the scalability challenge and how machine learning can play. But not answering a question for you, but how do you think about machine learning for security at Netflix?
Well, I think ML in generally is transforming multiple parts of our business. So whether it's content programming and production, using ML as decision support to figure out what shows do we want to make, making the process of producing those shows more efficient. On the consumer-facing side, we use ML to personalize the service and optimize the delivery service. But we also use it in the security space on the consumer-facing side for things like fraud detection, account takeovers, things like that. Increasingly, we're also using it on the corporate side, where we're using it to understand data access patterns, application access patterns, and then identify anomalous activity that might indicate malicious behavior. So it's a big issue for there, but it's transforming pretty much everything.
Awesome. Steve, machine learning for us, I mean, that's
So our
massive.
experience in building Amazon Macy, as you're really aware, has taught us that it is the single most effective way to increase the efficiency of our staff and make sure they're focused on that which really matters. GuardDuty, of course, launched based on a machine learning engine as well. And I think what you'll see is a continued effort in that space where we're using machine learning to help whittle down that which we have to look at from a security perspective.
So given the size of both AWS and Netflix, I mean, how do you plan and build for scale? When you think about security at scale, like how do you focus on that? And where do you focus the energy?
Well, a cornerstone is getting humans out of the loop and automation. That's obviously part and parcel of doing that. But when we think about scale, we think beyond just sort of the number of instances and traffic and data volume. But we start to think about how do we accommodate a growing and diverse set of developers who have different goals, they have different constraints, they have different knowledge and expertise in different parts of the infrastructure, and we want to make it easy for them to buy into what we're trying to achieve from a security perspective, to do the right thing in an easy way. And the main model we have for that is what we call our paved path framework, which is we invest in generalized tooling and infrastructure across multiple domains. It could be telemetry and logging, it could be continuous deployment, et cetera. And then we weave through that automated security components. So developers are super excited and motivated by getting their features out, launching their applications, having a fast pace of innovation. So they're motivated to use the paved path approach because it gives them that benefit in cases. And then the security stuff just sort of comes along for the ride. And that's a super useful way to think about how we scale that.
No, it's awesome. Steve?
I think this is one of this is sort of the same thing of building the fundamental components that help people practice security properly underneath, and ties back to the part I was saying about developers really want to do the right thing. So if we can give them tools that help do things well in the right fashion, it makes them go faster, they deliver better quality code, we have to do less work to remedy problems in the back end. Works for everybody.
Totally true. So one thing I do have to stress about Netflix is they are a phenomenal partner. They work really closely with our services as we go through beta process, and one of those processes was a Macy Hack Day. So you want to talk a little bit about it?
It was actually a general hack day we had. We do these regularly, and this last one we had a great opportunity to bring developers from the Macy team, have them pair up with developers on our side that were building a new application called Exploit Monkey, and it's part of our broad simian army, if you've heard about Chaos Monkey or the various different monkey tools that we have that are used to simulate real world events, and we run them against our infrastructure and see how well we respond, how resilient we are. And Exploit Monkey is introducing security conditions, replicating hacker attacks or security faults. And what we did is we wired the team actually wired Macy into Exploit Monkey. So when we would inject a security fault, Macy would detect it and that would flag it back to Exploit Monkey. Exploit Monkey could then suppress notification based on that because it would say, hey, look, this is just a test. But we'd also be able to test the accuracy, the correctness, and the speed at which we were responding to security issues. And that's, I think, a great example of taking this heavy lifting that you guys are doing and investing in at scale, and then pairing it up with sort of an application-specific implementation using our specific infrastructure and our needs. So it was
Awesome.
a great collaboration example.
No, I mean, you guys, in terms of a partnership perspective, I can't say enough. I mean, being on those calls and just getting the feedback, you made a lot of difference around GuardDuty and around with Macy, so we thank you for the support.
It's been a great partnership. My only complaint is that we hadn't had beer at this event.
Where's the beer? Where's the Harley? In any event, we're out of time, but thanks for sticking around. Really appreciate you guys being here tonight. And with that, I'm going to welcome Peter DeSantis back to the stage.
All right. Thank you, Steve, Jenny, Greg. It's very cool to see how Netflix is using some of our security services to solve their at-scale security challenges. Now, we've gone over, so I'm going to be quick here. I just want to thank again Dr. Matt Wood for his presentation, Brian Williams. I learned a lot on both. But I really want to thank you, not just for coming tonight, but for coming to reInvent. Your passion and your participation is what makes this event so special. Okay, let me wrap up. I promised you that I'd have a few suggestions for topics that you might want to dive deeper on. You probably weren't expecting homework when you came here tonight. But here you go. These are my suggestions. There's lots of other great sessions out there, but these will really auger in on some of the things I talked about tonight and give you the next level of details. All right, that wraps up Tuesday Night Live for this year. Thank you for coming. Enjoy the rest of your week. Enjoy the rest of your evening. Take care.